Welcome friends. So today we will see very important topic of algorithm, and that is nothing but asymptotic notation. So first of all I would like to ask you all, suppose you are writing a bunch of algorithms, you have more than one algorithms. But if I'll ask how will you compare two algorithms, so what would you say? There are many different aspects like time complexity, processing power of the CPU, stack space, RAM space, and hard disk space. Stack space is very important in nowadays because of the recursion of the function. It occupies the space in the stack. RAM space is very important aspect. Hard disk space is not that much important because we are having available at very lower cost bunch of hard disk. But still, when we will be talking about the space complexity, it is default understood as a stack space complexity. So main two different aspects, main important aspects to compare algorithms are time complexity and space complexity. So when picture comes about the time complexity, here the asymptotic notation comes into the picture. So let's see first how the different kinds of time complexity are there. Basically, two kinds of time complexity are there: a priori and post priori. Now, what is the difference in between these both? In the a priori algorithm, you are first evaluating algorithm. It gives you approx answer how much time would it take for the execution. Approx estimation would be there, and after it has been checked on the hardware. So when you enter your algorithm, it processes on the hardware, and it can then give you exact results. So with a priori algorithm analysis, you can compare two algorithms, like how much approx time difference would be there between two algorithms. While in post priori algorithms, you are simply inserting algorithms into your machines, and after processing, you are coming to know about the exact results. It takes this much time. Both have their own advantage and disadvantages. Like a priori algorithm is not that much accurate, but as it is hardware independent, like before entering to any kind of system, you are comparing to algorithms. That is very important aspect. And the post priori is hardware dependent, but it is more accurate. So both have their own advantages and disadvantages. Nowadays when you are working with algorithms, you work with only a priori time complexity in most of the cases. So you will see always the asymptotic notation when you have a priori time complexity comes into the picture. So asymptotic notation is nothing but time complexity which represents based on a priori algorithm. So let's see how the asymptotic notation works, but mainly which are the types of asymptotic notations. First of all, big O notation, big omega notation, small o notation, small omega notation, and theta notation. Don't worry, we don't need to learn every notation. Like if you will learn a single notation, you will easily come to know about the other notations. If you will just understand one notation, all others are not difficult, right? So we have to just focus on just one notation, and we'll easily come to know about the other notations. Okay, this is a very important line. I have come to know about, like I have concluded from my experience. Just read it carefully. Asymptotic notation is not about which program has less number of lines and which has more. It's all about how any program's number of lines rapidly increases at the time of execution compared to another program when we increase number of inputs. It means, like if you are like you are shown one program with 2 lines, one program with 4 lines. Not the program with the 2 line is more optimum. After you are going to execute, after the execution, how many lines are executed, and with the increase of number of inputs, how this execution line is increased, that is more important. So be focused on this thing. The concepts will be clear if we focus on this. Okay, let's see. Let's start from very simple thing. uh, I would like to make you imagine about the asymptotic notation with very simple example. Like if we are having, suppose, one building with 5 floors, and we have a thing in mind, like we already know the y. What is y? That is floor number of John, that is 3, that's fixed. And now we are confused about the floor number of Maurice. We are asking the people, like, do you know the floor number of Maurice? You know? And some people says, we don't know exact, but the floor number of Maurice is probably less than or equal to floor number of John, like third floor or lower than third floor, or third floor or greater than third floor. Like this answers we get. So whenever you get such relations like less than or equal to, always relate it with big O notation. I'll explain you how, but just this keep in mind. When you have less than equal to, relate it with big O notation. And when you come to know about greater than equal to relation, you are having the big omega notation, where x is you are having what function you are already having. So just otherwise it would be inverse. That's why. So you will come to know in just few slides. Let's see. Here I have given a table. We'll understand what is big O notation. Here the different inputs are there. Like if you are going to sort with any algorithm, the number of elements you are having for the sort, that is number of inputs. The one function n square, and another is 2 raised to n. You can see here there are different like sometimes f will be greater than, sometimes g will be greater than, if you will compare both at the same number of inputs. But after one point, that is here the row number 4, after one point you will come to know that there is always the g function dominates f function, like g is always greater than or equal to f, means you can say you are having the function f, so f is always less than or equal to function of g after some point, and that is point is here 4. You will, if you will go through more than these inputs also, it will not change, always f would be less than or equal to at any point of time than g. So in this case you can say that you are getting less than equal to relation, so you are having big O notation, like f is in the order of g. Yeah, f is in the order of g. I am repeating. Here you can see one mathematical and one specific definition of the big O notation. Some people don't like might don't like this definition, but now you will easily understand it. Like it's nothing but if 0 is less than, means it should be greater than function, that is nothing more than that. 0 is less than equal to function is less than equal to some function g. Here c is multiplied, just forget it for a while. I'll make you understand why c is there. Function, and if any function f is less than equal to c multiplies by function g for some positive constant c, then f belongs to big O notation of g, or you can say big order of g, wherever n would be greater than equal to k, means after point k it would go on, k should be always greater than 0, that's fine. So after you will find one point k, after that this function will be always less than or equal to the another function, so function f would be in order of g, that you can say. The same way, if you are going for the big omega notation, I said there would be not much difference if you learn the single notation. So here's two different functions, function f and function g. Function f is just n and g is 3 log n. Okay, now see the graph here. I'm sorry for this mistake that I have did the line 4 with the blue. I am really sorry. Actually, it should be the 10th line. Why? You can see sometimes the function f is greater than, sometimes function g is greater than. But after one point, and that is point g, after point, that is point 10, k equal to 10. After 10, you can see your function f that you have already taken. You can compare it with the different function with g, like f is always greater than or equal to g. So there is nothing more change in this definition. Here we are getting greater than or equal to relation. Like it won't happen at any point of time that f would be less than g. Even if you will take any number of inputs, that then and then only we can say that f is in the big omega of g. So here the definition is just a slight change. It's greater than or equal to rather than less than equal to. If your function you are multiplying with any c greater than equal to g, which is already greater than equal to 0 for some positive constant c, then function belongs to big O notation of g. Okay, and should be after any specific k you are finding, any k. Okay, now I know you will ask that Pratik, you told that these are the about the different functions, but how to go through this code? We don't have function, so let's see how to crawl a function from your code. Suppose I have taken one sample code over here. Now I will ask that how many times this printf will work. All the printf will work. So you will say how will you come to know here x is not given. Okay, x is not given. X is here nothing but number of input, right? Some people take n, some people take x. That makes no difference. But if we are sure for any x, the first loop will round around x square time. Okay, and the second loop will move for 4x time. So Printf will be printed for first loop is x square, second loop is 4x, and then perfect three statements will be printed. It doesn't depend on number of inputs, so 3. So here you are getting your function that is nothing but x square plus 4x plus 3. Now you exactly know how to crawl a function from your code, and then you can find the function which is in the order or in the big omega notation, right? So how to find? Let's see. Uh, let's take this the same function x square plus 4x plus 3 you have rolled from the code. Now I need to find big O notation. Big O notation means I need to find which relation less than equal to relation, right? Okay, so let's try to arrange in some way. Now whenever we'll speak, we'll always speak in the larger number of inputs. For larger number of inputs, we can easily say 3 would be less than or equal to x square, because we are speaking for larger number of inputs. So at one point will come that after that point you can take any x. Here you can, if you will take x equal to 1, this will not be satisfied, but if you will take x equal to 2, 3, 4, 5, 6, any x, then it will be always satisfied. 3 would be less than or equal to x square, right? So we are adding, the left term is already smaller, we are adding smaller term again on the left and larger term on the right, like this way. 4x plus 3 less than or equal to 2x square, that's true. Again we are adding smaller term on the left and larger term on right, so it would be continuously true. X square plus 4x plus 3 less than or equal to 3 times x square, right? Means the same term we have added, but it would remain same. So here we have added such terms on the left side just because we wanted to conclude our function f. So now we come to know that this left side is nothing but our function f, that is less than or equal to some function g with multiplying some constant. So here you can see what we were what we were talking about, that constant c. Here constant c doesn't matter because it's okay, you are multiplying with some linear values. It's okay, you are constant means you are multiplying with linear values, that's fine. You are getting any function even though you are multiplying it with the c, that's fine. But the main thing is it is in the linear relation to that constant, means here your function f is less than or equal to function of g. That's what you are getting about your big O notations. So you can say function f is in the order of g, or function f is in order of x square, because your function is nothing but x square. I am sure you will ask this thing me that oh, here you have taken x square. If you will take x cube on the right hand side, it will give you the answer that function is in the order of x cube. You're absolutely right. Why not? If I can say, see here at the top right side, if x is less than or equal to 3, then it's obvious that x would be also less than or equal to 4, less than or equal to 5, and so on, right? So whenever you say f is in, means function is in order of some function x square, so it's obvious function is in order of x cube, x raised to 4, etc. Okay. Now let's take one more example, x cube plus 7x square. For this, let's find the big omega notation. Okay. So here we need greater than equal to relationship. That's why we have started by this way. We want to crawl our function f. We want to evaluate the function f at the left hand side. So we will arrange it in that way. So x cube, it comes with the practice. Here x cube is greater than equal to x square. True? Fine. X cube plus 7x square is greater than equal to 2x square. That's also true, right? The same, because we added the higher value on the left hand side. So our function f is greater than equal to c times some function g, and here c is nothing but a 2, right? So we have got our big omega notation. F is in the big omega of g, or you can say f is in the big omega of x square. Okay. Now I'll ask that if x is less than equal to y, then obviously y is greater than equal to x. That's true. That this should be also true in this relation. Like f function is having in the order of g or big omega of g, then g is having, sorry, big O of g. F is having big O of g, then g is already having big omega of f. That also works, right? Actually in the definition, like they are writing belongs to, like function belongs to order of function g, f belongs to order of g, but they have now become a tradition that they have replaced belongs to with the equal to. So we'll also go on with the same way, like here we are writing f function equal to order of function g, right? But the real we can write it's belongs to. Okay. Now let's see how what is the difference between small o, this small omega theta? Now you know only one, you know one or two things. Now you will easily know the other things. That is just small difference. Suppose you are having here function f. You can see f is less than function of g, right? This is one relation. Here you can find like you can see the function f is sin x plus 1, g is sin x plus 4. The second side we can take one more thing. The only difference, what is the difference in left side and right side? Functions are different, that's fine, but here left hand side, the g function is not even touching the function f, means f is less than g, but at the right hand side f is less than or equal to g, right? So this is the difference between big O notation and small o notation. Here your k is defaultly 0 because at the initial stage, from the initial stage it goes on with this relation. So your left hand side is nothing but big O notation and right hand side small o notation. The same way small omega is there with greater than relation, right? So I don't think there is need to explain it. So let's come back to that slide. Here we can add a few more things like small o notations. You will have less than relation in your mind for that, and for small omega greater than. Okay, so the final things remaining, that is theta. What is theta? Theta is nothing but equal to, let's see, suppose I'll say where would be x equal to y? hmm? We'll ask what is this question. It's really where would be x equal to y? When you know that x is less than equal to y, and parallelly you are having x is greater than equal to y. If both these conditions are satisfied, you can say x equal to y, right? So same way, if I'll ask what is the theta notation, like what, where we, when we can say f equal to theta of g, you are absolutely right, when f would be in the order of g, as well as f would be in the big omega of g. So you can easily say f is in the theta of g. How? Let's take an example. Here function 4x square, just simply 4x square we have taken. So you can say 4x square is less than equal to 5x square. True. Okay. So it would be always true, right? After one point, like it would be always true. So here you can say your function f that was already given is less than equal to constant multiplied by function g. So f is in the big O of x square. Same way we are finding the big omega notation, we can write down 4x square is greater than equal to 3x square, because now we want to find x greater than equal to relation. So we need to arrange it according to that. This comes with the practice. 4x square greater than equal to 3x square. So it's obvious function, your function is greater than equal to constant multiplied by g. So here it's f is nothing but big omega of x square. So these both the conditions are satisfied. So you can say f is equal to in order in theta of g. So f is in theta of g. Fine. You have understood almost everything. Now just one question from my side. I am giving it these two functions, sin x, cos x. Just help me out to find out which is in the order of which. F is in order of g or g is in order of f. Can you do it? Let's see. You can see, if we will we will plot the function of sin x and cos x, it will go in this way continuously. So you will ask me, then how do we come to know who is in the order of who, right? Main thing is asymptotic notation don't satisfy trichotomy property. What is trichotomy property? If for the in the case of numbers, the trichotomy property is in the number x and y, there should be some relation either greater than equal to, less than equal to, greater than equal to. I'm sorry, I repeatedly did the less than, but there should be greater than. So there should be some relation between two values. The same way there should be relation between two functions in asymptotic, but asymptotic notation don't satisfy trichotomy property. So it's not always that you will find some way that one should be in order of another, one should be in omega of another. You might not find also, right? These are the properties basic of the asymptotic notation. You can see and evaluate by yourself also. Reflexive property, symmetric property, transitive property, transpose property, right? Suppose x is less than equal to y, so y is greater than equal to x, the same way. F is in the order of G, G would be in the big omega F. Trichotomy doesn't satisfy for the any of the asymptotic notation, that's obvious. Okay. Uh, so thank you very much. Thanks for giving your precious time. You can have any question, you can mail me on pratikcalling@gmail.com at any time. I'll try to reply you as soon as possible. Have any question about algorithm, asymptotic notation? Okay. Hope you like this video. Thank you. Thank you very much.